Good morning, everyone. Welcome to our second presentation of the day in St. Helens. Our speaker today is Pablo Alfaro. Pablo is a renowned machine learning engineer with over 15 years of experience in several different industries: meteorology, retail, and energy. Today he will be sharing with us demand simulation and forecasting models. And so let's give a warm welcome to Pablo.
Well, thank you very much for that presentation, and thanks to the organizers of PyData for bringing us all together here. It's an awesome opportunity to be sharing these experiences with you. So, well, I'm Pablo Alfaro. I'm a senior machine learning engineer. I come from a software engineering background and have a mathematical engineering master's degree. I have worked in the energy and meteorology industries. You know, in energy, I did some simulations and pricing optimization. And now I've moved to retail at Trio, where I'm the pricing solutions technical lead. So who are we at Trio? Trio Labs is an AI and machine learning consulting company. We specialize in developing the AI capabilities of our business partners. And you can see here some of the Fortune 500 customers that have trusted us with their projects. We have skills across the entire machine learning stack. We can do predictive analytics, computer vision, natural language processing, and MLOps. And we also have a strong focus on the pricing, and particularly in the resale industries. So that's what we'll be talking about today. Okay, let's start going headfirst into the pricing problem. First, who here in the audience knows a little bit about the pricing problem? Okay, well, nice. We can work with that. Okay, let's start with a little bit of motivation. Why do we want to do pricing optimization? And the answer is clearly to maximize profit, right? We do so in AI by leveraging data that we have on our customers' behavior, you know, to model their pricing decisions and use that to make better their purchasing decisions, and use that to make better pricing decisions ourselves. For example, a classical example of data-driven pricing is seasonal pricing, where jackets sell more in the winter, right? And then you can price accordingly. But more modern takes on that technology allows us to capture is, for example, competitor changes in prices, or you know, a YouTuber recommending our product. All of that can be used to enhance our competitiveness and gain a larger portion of market share. So what can we expect for a business impact? Well, McKinsey has quoted a 2 to 5% sales uplift is typical, with an accompanying 5 to 10%. And we actually have deployed such technology in one of our customers, and they were expecting a 1% increase in gross margin, but we managed to deliver 28%. So as you can see, the gains can be pretty significant. Okay. Given that motivation, what is the actual pricing problem? And pricing optimization, in a nutshell, is maximizing the profit function, which is that function you see there that's composed of two parts. Essentially, we have this blue part, which is the demand. You know, that is going to be affected by your pricing decision, as well as several other factors that we can incorporate as covariates. And then you have your unit margins, which is prices minus costs, essentially, right? The higher your price, the bigger your margin. But conversely, the lower your demand, right? The higher your price, less people are going to be willing to purchase your items. So you need to find the trade-off there that maximizes your total profit. Okay, so a bit more motivation. Why do we want to simulate a market? And there's essentially, you know, three big things that come into play. First of them is the expectation. You know, in a simulated market, you know what should happen, what should be happening in it, and then you can define a clear target for your models to pursue. Then you have reproducibility. This is super important. In the wild, it's very difficult to observe 2 times the same situation, unless debugging and tuning models becomes very difficult, because you can't really you know, adapt to the same thing. The final thing is actually measurements rather than regret, but regret is the most important measure that we'll be taking. And that is, I know, you know, in this theoretical simulation, I know what's the maximum I could have gained if I had perfect information. You know, if I knew the underlying truth, I know what I would have gained. But since I have an imperfect estimate, I will make some, you know, delta below that. Right? That difference I want to bound and minimize, essentially, in order to have a guarantee that my models are going to perform well in the wild. If I don't have that, I can put out models in production that can have costly mistakes and lead to large losses. So, okay, let's go into our market simulator. And before we start building it up from scratch, we're going to define a few assumptions regarding its scope. So first, we are going to, have some simplifying assumptions, and let's get into them. So we'll have a single item market that will have no competitors and unlimited supply. And you can see these are fairly restrictive conditions, right, that limit the applicability of this simulation. But we actually deliberately chose those situations because we wanted to build a simulator that was fast to develop and that could lead us to, bring modeling improvements in a short time frame. We were aiming for a 3-month delivery, right, in terms of modeling improvements. So we wanted a simple to build simulator versus a more complex, simulation that would take years to tune and properly model. And I hope by the end of this conversation I can convince you that this was a good approach. What we didn't want to sacrifice, though, is that the expected demand is a function of price, obviously, right? But also from other covariates, other factors that may be affecting our simulation, right? You can have seasonal effects, you can have trends, you can have, other factors that determine the number of sales your customers are going to purchase, and we want to be able to model that. And the final thing is randomness, which is we won't ever be able to observe every factor contributing to the pricing decision of our customers, and the final outcome is going to be a random realization of our expected demand. We'll see what that means very shortly. Okay, so let's get into it. This is the first component of our market simulation, which is the expected demand that we can expect to sell as a function of price and covariates. And don't worry about the formulation, that's there just for reference. But what matters is the curve to your right, which essentially has the shape of the curve that we're producing. And you can see that it has some good properties for modeling a demand curve. Essentially, it is monotonically decreasing with price. So the higher the price, the lower I sell. It has an elastic region where demand varies heavily with prices, right here in the middle. And then price dominates exponentially, right? No matter the value of alpha, if I increase price high enough, I will kill the sales. So this is important for us to be able to model. And using the parameters in this function, we have alpha is a proportionality constant. So increasing that value means we sell more units. Decreasing it means we sell less. And then we have beta for the slope and gamma for the center. We can create a lot of different markets for different kinds of goods, right? And using alpha as a function of x, we can incorporate any covariates that we want. Okay, so we have expected demand. Now, what about expected profit? This is what we're going to be trying to chase. So expected profit is no more than multiplying the expected demand times the unit margin, right? And then we add to our simulation this red curve here, which essentially is the money that I can expect to buy if I price at that point in reality, right? The blue dot here at the top is the true optimum expected profit that I can achieve, and its corresponding price is the corresponding optimum price, right? That is what we're going to be targeting, essentially. We want to get to that price. Okay, we talked about expected demand and profit, but in reality, we won't, even though we may expect to sell 2.5 units of a product every day, we won't really observe, 2.5 units sold on any given day. We will observe 2, 3, 4, whatever, right? But an integer number. So in order to model that, as well as that uncertainty in the customer's decisions, we will use a Poisson distribution from which we'll sample. And the trick here is that we will use the expected demand that we defined before as its conditional expectation. So we will have different conditional expectations for that Poisson distribution from which we'll sample our realizations. And I don't know how those come across in the projector, but here are some little green dots with a truly high alpha. Those green dots are the realizations of the sales that we will be observing. Our goal as pricing agents in the market is going to be estimating the blue curve from those green realizations, right? And yeah, and I'm getting ahead of myself. So this is the learning agent, essentially. How are we going to get the blue curve? Well, we're going to do that by using a regression problem. Essentially, we will have the number of units we sold as a function of the price, the covariates, and a set of model parameters, and we will fit those model parameters in order to minimize an error term, right? That way, our function f will try to match as closely as possible the number of units we sell, and then we can use f of price and covariates to forecast what we'll be selling. Okay, so we keep adding components to our simulation. Now we have a light blue line. So this staircase, light blue line, is essentially our forecasted demand, and that is trying to track the blue underlying demand. And then we have the pink line here, which is the forecasted profit, trying to track the true red profit, essentially, right? And here at the top, you can see this orange dot is essentially our suggested optimum price, right, corresponding to the maximum forecasted profit there, right? Our optimization problem is going to be choosing the top point in that pink curve, right? Okay, so we have all the components we need to define our simulation. How do we tie them all together? Well, we have this simulation loop, which is essentially a closed loop in which we'll start from a set of market conditions that is essentially, our history of pricing, what we did in the past. That is going to produce the data set that we need to train our regressor, essentially, right? And we will use that data to train our regression model, which we'll in turn use by varying the price across the entire x-axis in order to produce that forecasted demand curve. Now that we have the demand curve, we optimize the expected profit as a function of price. We make our pricing decision, and we set that upon the market, right? After we set that on the market, we observe the market reaction, and people purchase a certain amount of goods from our company. That in turn generates a new data point, which we can use to further refine the model, and the cycle continues, essentially, right? So how does it all play out? Well, like this. Here you can see that the model is essentially trying different price points, and as it tries new prices, the estimate of the blue curve gets closer and closer to the true underlying demand, and then conversely, the expected profit also gets closer to the forecasted profit gets closer to the expected profit. And finally, we come up with the optimal price decision that matches the blue dot more closely. Okay, so we've done it. We're true. I mean, we have a pricing model that can solve all our problems. Well, not quite. Actually, there's a few scenarios where this same model won't be able to converge. And if you notice here, we have our y-axis ranging in the 0 to 250 units, right? So that means we have a fast response from the market. That market purchases a lot, and we have a lot of elasticity. So if we make a bad pricing decision, we're going to see that immediately. Whereas here, our market tops out at 0.25 units per day. So essentially, this is a slow-selling product, and that becomes a problem because we can't tell whether we didn't sell the product because we set a bad price or because the product naturally sells slowly. So what it produces is that we will, whenever we see a sale, like a confirmation of sales in any price point, the model is actually going to stay pricing there because it thinks it will never sell anything at this location. And so it will be stuck in a suboptimal region. And even though we get perfect accuracy in this region, we will never get to explore this, right? It will be stuck there forever, missing the optimum altogether. So, okay, we have an exploration problem. And what that means is that we cranked the difficulty up a little bit more, and we defined 9 different scenarios for our agents to try to price on. And the scenarios don't matter that much. It's different locations of the historic prices with regards to the true optimum price. And then, a fast sales demand curve, a slow sales demand curve, and another kind of curve that doesn't have a flat zone to the left. But essentially, out of these 9 scenarios, we only managed to get good results in 1 of them. So imagine our wow at that moment. We were not super thrilled, but at least having the simulator allowed us to surface this problem, right? That was true in our actual models. So, okay, we know that we have a problem. We know that it's an exploration problem. And how can we work around that? How can we solve it? Well, to do so, we will, borrow from inspiration from the multi-armed bandit problems. Who here in the audience knows about multi-armed bandits? Okay, cool. Well, multi-arm bandits is a pretty cool and super simple, actually, reinforcement learning algorithm in which you have several, slot machines. Each of them have a different payout, right? And we, as agents, need to determine which of the machines pays the most, and we can do so by trying them out, and figuring out which one is the better paying one, right? To do so, what we'll do is we'll build an estimate of the distribution of the expected payout of the machine. And as you can see here, if this red line is the true payout, a bad sample, right, if we got unlucky and got particularly high samples for this machine, can lead us to the same problem. We can, get an estimate that's higher than the true value and a lower estimate in the true maximum, right? And we will forever keep trying this arm because we will only be focusing on the expected payout here. So the way bandits work around this, and I'm so glad that the Nixla guys came after me because they explained to you all you need to know about confidence intervals, is by using confidence intervals, essentially. We're going to use an algorithm that's called upper confidence bound, which is built on the principle of optimism in the face of uncertainty, which is actually a pretty cool thing. And it essentially states that if you don't know what will happen, you're going to be optimistic about it and try it out. See what happens, right? So instead of using just the average of the distribution, we're going to take the entire distribution here, right? And we're going to look at an upper bound of that distribution instead of looking at the mean. This upper bound incorporates the variance that I have in this box, essentially, right? And what I'm doing here is explicitly favoring exploration. If I don't know what is going to happen, I'm going to try that out. If I was right, then that means I will get a higher payout here, and this estimate is going to go up, so this arm is essentially going to become more attractive over time. If I was wrong, then I will diminish my uncertainty, because the more samples I get, the less uncertainty I have around the mean, and then I can, ignore that arm, essentially, because that's not paying enough. Cool, so with that we have an exploration algorithm, right, that can, explicitly reward exploration. So, okay, bandits use the number of times an arm has been tried to determine the confidence interval, right? But here we have a slightly different problem. Prices are continuous and not a discrete arm, right, like in the bandits problem. Well, we could beam prices and build, discrete sets of prices that we could try, but then we also have the covariates. So we would need now to beam both the prices and the different levels of the covariates, and that is going to lead to a very sparse data set from which it's going to be very difficult to learn anything, essentially. So the question becomes, how can we build a confidence interval for an arbitrary model? And we find an answer for that in a classical statistic technique, which is bootstrap. What is bootstrap then? Well, bootstrap is actually a way for us to estimate the distribution of any parameter that we can sample multiple times. And if we see our model's forecast as a random variable that depends on the samples that I have on my training set, we can estimate the distribution of the expected forecasted profit, essentially. So we do that by subsampling our original dataset. We build multiple bootstrap samples with replacement. There's a proof for why that works. But essentially, we're going to chop our original dataset in multiple subsets with replacement. We're going to train different models on each of those subsets and produce a forecast for all of them, hence getting a distribution of the forecasted expected profit. And then using any, we can extract from that distribution any parameter that we want, in particular a high quantile. Okay, and I'm going to show you what that looks like, but first I'm going to make a little disclaimer. There's a lot more tricks that we actually needed to make this converge. We won't be able to cover them here because of timing, but if anybody is interested, I'm more than happy to chat about it afterwards. I just wanted to enumerate this here for you guys. Okay, and so here's our simulation again. What we have added now is these shaded areas that you can see here. And those shaded areas essentially correspond to the bootstrap quantiles. So what we did here is we trained 30 models instead of 1 and produced a forecast for each price point on each of those 30 models, right? Getting a distribution of forecasts. And from that, I extract the 50%, 60%, 70%, 80%, 90%, and 100% quantiles. And those are the borders of the shaded areas that we show in the plot, right? And if you notice, the areas where we have the least data points usually have the widest confidence intervals, right? That is our uncertainty. We're quantifying uncertainty because we know less what will happen there because we have fewer samples. So essentially, we managed to get what we want with this bootstrapping technique. And how does it look like now? Well, like this. You can see that the model is no longer stuck in that high sales single observation, but rather is now trying across the entire price range. And as it does so, it is converging towards the region of the optimum, getting more performance here in particular, being more accurate at determining the demand curve around the true optimum. And one thing that's important is that the difference that we want to measure is the difference between where the orange dot would land in the red curve minus where the blue point is. That is essentially our regret, right? It's the difference between the maximum that we could have achieved and what we actually have achieved. So as you can see, in very few steps, the model is actually pricing where it gets to this very flat region of the profit where the differences are minimal. So that's good. We actually are hitting, the optimum in terms of profit. Okay, and this plot is actually here to show you, what we are capable of doing with having the simulator. We now can pit our model against a multitude of simulation scenarios, all in parallel, right? So that we can, observe the model's strengths and weaknesses, understand what is going on, what is wrong, and speed up essentially our development cycle, our research and development cycle. And it's not the idea that you guys focus on every plot at once, but what you can see underlying all these plots is that the model starts trying out prices, and as it does so, it starts getting a more and more accurate estimate of the blue curve, right? Which in turn leads it towards being closer to the optimum, and essentially all the orange dots end up converging to the true blue dot. And so here's our results table again, and now all those red ticks have become green, all those red crosses have become green ticks. So what do we have here? Well, we are tracking the cumulative profit lost since the beginning of the simulation. Essentially, that difference between within where the blue dot is in the red line and where the orange dot would have landed in the red line in the profit. So our regret, essentially, how much did I lose in terms of profit on every step, and the percentage of that accumulated across the entire simulation. And we never lose more than 5% on the maximum that we could have gained on any scenario. So that's a pretty good result. And the only thing that's left for us to do is that this guy here actually got, the other metric that we track here is how many steps we lost more than 5% of the true optimum profit. And this guy here got stuck in a super high sales number in a too low price. It eventually managed to realize that price point was not going to pay that much, but since it got a super high number of sales for one bad realization, it got stuck exploring that price too long. Still, in the red crosses table, this number was 1%. So 80% is not fantastic, but we're much better than we were before. So, okay, some closing remarks. Well, I wanted to end this presentation with a quote by George Box, which says that all models are wrong, but some are useful. And that is kind of the justification for the choices we made when we designed our simulation. Essentially, we wanted a simple model that we could build, and use that to start gaining insights on our true models, which is what we are actually building. So what have we achieved during this presentation? Well, we have presented some key pricing concepts and built a simple but expressive formulation of a market simulator that allows us to model several item realities. We've defined and implemented a naive pricing agent and used the simulator to find its limitations and find scenarios in which it wouldn't work. We generalized the upper confidence bound algorithm to an arbitrary agent that can include covariates and can manage to balance exploration and exploitation, exploring the true demand curve and finding the optimum location there. And we used the simulator to validate our claims among the diverse range of market scenarios where we got excellent performance, leading us to be happy. So Well, that's all I actually wanted to show you. If anybody's interested in knowing more, we have this blog post series that's called Mastering Pricing Strategies. That's on the Trial Labs blog post. We have the first blog post out already, which covers, the building of the simulation. And then we're going to develop a few more of these ideas regarding Bootstrap and that there. So if you guys are interested, you can check that out. So that's all I had to say, and I'm open to questions.
Hey, thank you. That was pretty cool. Can you talk about markets that are non-monopolistic, where you have competitors?
Yes. Well, actually, we have in our. Oh, well, let me. No, the question is recorded, right, in the mic.
Yeah.
Okay, the question was about non-monopolistic markets where we have competitors. So we have in our roadmap for the simulator 2.0 a way to incorporate competitors in the simulation. And the way we want to do that is we will have an arrival rate of customers to our market, right? So every some time we sample a new customer reaches the market. That customer is going to have an evaluation function of all the offers that are available in the market. So price is going to be a factor there, but then also is going to be, quality of the good I'm selling, my ratings, my antiquity as a seller, right? Several stuff that can guide the customer's pricing decision. The customer is going to compare his valuation across all competitors and keep the competitor that has the maximum valuation. And then he's comparing that valuation against his own threshold, and if the valuation exceeds the threshold, he makes the purchase. So with that, you can incorporate competition into your market simulation. And the tricky part about that is that you need to build your engine to be event-oriented instead of every fixed time steps like we have here, which is much simpler, right? So that's kind of why we didn't get into that yet, but we have it in our roadmap for the next iteration. Yeah, totally.
Any other questions?
Maybe an interesting remark behind competition markets is that you have a hyperelastic zone in your demand curve. When you reach the competitor price, essentially your demand drops to zero, or a little bit higher if you're a good seller, right? But your demand drops to zero very sharply. So that is a complication for the regressor agent to learn the demand curves. Yeah.
How do you handle codependence, where the price of some products might influence the price of other ones that are natural complements to it?
Right. Yeah, that's another thing that we wanted to explicitly avoid with the single item market. That's a tricky one. And essentially, the way we've been working around that is by incorporating, the best way we've found to incorporate that into the learner agent is by manually defining a set of competing products. You need to use some clustering techniques in order to determine that, my sales go down when these sales go up, or conversely, right? And then you have this set of competitor products, and you can incorporate, statistics about their distribution of prices into your covariate set. So you can do, for example, the average price of my competitor products, the maximum price, the minimum price, right? All of that. And with that, you give your learner agent an idea of what products that are complementary to yours are doing, and that can help you, understand its demand. Yeah. But simulating that is a lot more tricky because you need to, specify the dependence in demand between those products, and getting that right is a lot more difficult.
Yeah, thank you for the presentation. So I see most of your slides were doing the analysis between the price and the demand, right? So are there any other factors or variables to be utilized by the simulator to reach to the optimal pricing point?
Right. Well, that's also in our roadmap. We haven't covered yet incorporating the covariates in the simulation, but we already have implementations for incorporating like seasonal patterns within the demand curve, right? We will vary the alpha so that it can go up and down every seasonal cycle. We also want to investigate trends and shocks something abrupt changed and demand has jumped to a new location altogether, starting this time step. And what we expect is going to be useful there is forgetting the past, essentially. I can't, base my demand curve estimates based on what happened like a year ago. I need to learn from what happened in the very short term so that I can adapt faster to those kinds of signals.
How does the model handle things where you have very sparse data sets? So where it's a brand new item, so there aren't a lot of sales and there isn't a lot of observations for price, or where price just doesn't change very often?
Right. Well, there's two parts to that question. So the question was about how do you handle a sparsity in the data set, where you have few observations of prices for the item or even none, right? The first thing you can do is find similar products that, and similar comes in terms of other covariates that you may have, right? We used to price for a clothing company, so, scarves would have more or less similar components, right? Things like those can help your model understand demand of the new product. Then the other thing is that having an exploration agent is super important because it allows you to actually discover the data that you're missing. Right? So that's kind of what I was trying to tell you, that we found that usually the past data is a very poor representative of the true underlying demand curve. And you can see that in that scenario here. Oof, I blew past it. Here. Like, if you see these dots, you would never say that's the demand curve right underlying that. But so the agent essentially starts with data that's not representing what you want to estimate. So the exploration component of the agent plays a key role in discovering those prices. Yeah.
Thank you for the talk. I had a more technical question in terms of what libraries, and I assume Python, since you're here, that you're using to this and your experience with them.
Well, for building this, it's pretty much NumPy and XGBoost, and we have a little bit of pandas because it makes it easier to keep track of what variables what. But essentially, it's only that. We are actually looking into conformal prediction because Bootstrap has the disadvantage that it's slow. You need to train 30 models in order to get that distribution. So conformal prediction seems like a good opportunity to make that distribution estimate a lot faster. So we're looking into that. And the other things that we want to try are things like AutoGluon that was presented here yesterday as well, right, where you can have a bigger battery of models trained to do the regression problem. Yeah, but that's more or less it.
How did you do the simulation? Which tool did you use the simulation part?
So we built it from scratch using NumPy, pandas, and XGBoost mostly. We started from the other way around. We used the template method, the programming, like the design pattern template method, where we built, each of these steps in the simulation loop as a placeholder, and then we started filling out, what needed to happen in each of these steps of the simulation. And we have a framework which allows swapping one model for the other very simply, right? Stuff like those. Yep.
Any other questions for Pablo? Awesome. Thank you, Pablo. Can we give a big round of applause?
Thank you very much.